Welcome to the Fall Asleep Fast channel. On this night, when the stars are whispering, allow me to use this bedtime science video to lay out a cosmic blanket for you now. Please close your eyes and imagine we are riding the moonlit boat of an astronomy bedtime video, drifting in the cradle of the Orion Nebula. Those twinkling stars are not distant scientific symbols, but a customized lullaby of constellations just for you. The heartbeat of Betelgeuse transforms into pulsating rhythms. Jupiter's clouds swirl with milky light vortices, and Saturn's rings sing billions of ice crystals into a cosmic cradle song. The acceleration of the Milky Way's rotation syncs with your breath, and the dust left behind by supernovae reconstructs into the fabric of dreams during meditation. We are no longer mere observers, but stardust floating in the afterglow of creation, letting Einstein's curvature of space-time gently envelop your weary neurons. As the Pleiades bloom with blue light in your mind, allow the boundaries between scientific principles and dreams to dissolve tonight. There is no need to ponder the singularity of black holes. Simply let the waterfall of light from the Andromeda galaxy wash away the day's distractions. For all unsolved mysteries will transform into metaphors for slumber within the starlit cushions of the sleepy science channel. Good night, dear cosmic wanderer. May this bedtime science video escort your consciousness into a sweet dream, more serene than dark matter. 34 kilometers per second, antenna locked on Earth for the final 57 seconds. 3,000 degrees Celsius flames, and soon 13 years of watchful waiting. A 7 billion kilometer journey, fuel exhausted. The mission is about to end the final descent phase. He weaves between the rings. What did he see? We hope this video can wash away the fatigue of your busy day. Watch quietly, listen quietly, and we wish you pleasant dreams. Speaking of the legend of Cassini-Huygens, it holds great significance for humanity. Although 4 unmanned probes have visited Saturn before, Cassini-Huygens is undoubtedly the most impactful among them, whether in terms of physical impact or scientific contribution. The data it sent back laid the foundation for over 4,000 research papers. It discovered 6 previously unknown moons and helped us better understand their composition. It traveled 7 billion kilometers over 20 years, spending 13 of those years around Saturn and its environs, continuously collecting data on Saturn's gravity, magnetosphere, rings, and their structure, until its final moment, as it plunged into Saturn's mustard yellow clouds, ultimately shattering into countless fragments. Cassini was still collecting data, coupled with providing the most stunning images of Saturn and the solar system to date. This was undoubtedly an exceptionally great mission. The first probe to reach Saturn was Pioneer 11 in 1979. It was at that time scientists confirmed that Saturn's largest moon, Titan, also known as Titan, possesses an atmosphere. They realized they had to return to this moon, but this time with a lander. However, at that time, Voyager 1 and 2 were already en route to Saturn. Therefore, adding a lander to these 2 missions was naturally too late. Thus, Cassini-Huygens was born. Launched on October 15, 1997. Sending a probe to Saturn isn't simple. The entire journey fights against the sun's gravity. Therefore, to gain the speed needed to reach Saturn. Cassini used planets for gravity assists. It flew by Venus twice, then returned near Earth. Earth's gravity then acted like a slingshot, flinging it towards Jupiter. Jupiter provided the final acceleration needed to reach Saturn. This specific planetary alignment enabling such gravity assists occurs only about once every 600 years. It truly seized the right time, place, and conditions. Moreover, Cassini's distance during its second Earth flyby was particularly perilous. Its closest approach was only 1,100 kilometers from Earth's surface. Even more interesting is Cassini's power source. It was powered by 3 RTGs, radioisotope thermoelectric generators, essentially. Its energy came from about 33 kilograms of radioactive plutonium-238. This radioactive decay provided Cassini with power. Even towards the end of its mission, it could still generate about 700 watts. The reason Cassini used RTGs was that solar panel technology wasn't advanced enough at the time to provide sufficient solar power for a probe so far away. With RTGs, Cassini achieved a very long operational life. If it hadn't eventually run out of propellant, it might even still be working today. Cassini had multiple objectives: understand the structure and dynamics of Saturn's rings, more comprehensively explore Saturn's moons, measure Saturn's magnetosphere, study Saturn's atmosphere, and study Titan more deeply. This last part is precisely the origin of the Huygens in Cassini. Huygens was a lander attached to the Cassini orbiter, designed to detect what lay beneath Titan's hazy clouds. The Huygens probe was built and operated by the European Space Agency. It was only about 1.3 meters in diameter and weighed about 300 kilograms. After separating from the orbiter, it drifted in space for 22 days before entering Titan's atmosphere. During this time, the only system running on board was a wake-up timer set to activate the probe just 15 minutes before atmospheric entry. When it awoke, the sight was astounding. This video is an accelerated version of its 2.5-hour descent process. Huygens's primary mission was actually centered on this descent. It was responsible for measuring atmospheric pressure, composition, wind speed, and other data. As the mission was limited to atmospheric measurements, its battery life was not expected to last long after landing. Scientists had envisioned it might land on an ocean or lake, so Huygens was designed accordingly. But judging from what you see, the place it actually landed was likely a dried-up lake bed. Cassini's own mission was an outstanding success. Beyond the scientific data collected over the past 13 years, it also provided some of the most breathtaking images from space. Of course, Saturn's moons themselves are each fascinating. Someone specifically compiled 1 million photos taken by Cassini, showing us the view as if we were on the Cassini probe itself. These are all real images, only color corrected and enhanced, and sequenced to show motion. With no computer-generated imagery, it's simply magical. As Cassini's fuel gradually dwindled, scientists began thinking about how to maximize data collection in its remaining time. To this end, they sent commands to Cassini, instructing it to perform a series of very close flybys of Saturn and some of its moons, closer than ever before to Saturn and its rings. Starting on November 30th, 2016, Cassini repeatedly climbed high above Saturn's north pole, then dove down to a point just past the outer edge of the narrow F ring. It completed 20 such orbits in total. Then, on April 22, 2017, Cassini would cross over the rings to begin its final series of daring dives, weaving between the planet and the inner edge of the rings. This was Cassini's grand finale. A series of orbits and dives brought the probe ever closer to its subjects simultaneously with each flight. It faced increasing danger until finally, just as its data became the purest, the moment Cassini flew into Saturn's embrace, its fate of destruction was sealed. NASA's website explained the reasoning behind this final mission. During the grand finale dives past Saturn, Cassini will collect some exceptionally rich and valuable information. This might be something the original mission planners never imagined. The probe will map Saturn's gravity and magnetic fields in detail, revealing the planet's internal structure and potentially helping solve that tricky puzzle. Just how fast does Saturn's interior rotate? It will greatly enhance our understanding of the total mass of material in the rings, bringing us closer to understanding their origins. Cassini's particle detectors will sample icy ring particles being guided by Saturn's magnetic field. Into the atmosphere, its cameras will capture stunning, ultra-close images of Saturn's rings and clouds. No previous mission has explored this unique region so close to the planet. The knowledge we gain from these activities will help improve our understanding of how giant planets and planetary systems everywhere form and evolve. At the end of its final orbit, as it plunges into Saturn's atmosphere, Cassini will complete its 20-year mission by ensuring potentially life-bearing moons Enceladus and Titan remain uncontaminated. This is an exciting and romantic story, a perfect ending for this legendary exploration tale. But let's look closer at these final moments. During Cassini's grand finale, NASA was willing to sacrifice Cassini's remaining operational time in exchange for an unprecedented close approach to Saturn. After all, Cassini's fuel was nearly exhausted, so its survival was not a consideration. Making this decision meant Cassini was authorized to get closer to the planet than ever before, weaving between the rings. But what did it see? Did this unique perspective reveal things we had never seen before? Let's look at some of the spectacular sights Cassini saw during the grand finale. First, regarding Saturn's moons, it saw some of the shepherd moons in unprecedented detail. Here is a close observation of Atlas, a 40-kilometer diameter moon located near the outer edge of the ring. What's remarkable about this moon is its seemingly smooth surface, lacking impact craters, giving it an extremely peculiar appearance. Dust from the rings is accumulating on its surface, especially around the moon's equator, smoothing its surface and giving it this disc-like shape. A similar situation occurs with Saturn's second innermost moon, Pan. It's about 30 kilometers wide, located within the ink gap. Any ring particles straying into this 350-kilometer wide passage are swept up by pond. This keeps the ink gap stable and constant. Daphnis is another shepherd moon. Unfortunately, it wasn't captured in such detail, but due to its location within a ring gap, its influence extends hundreds of kilometers. It is only 8 kilometers in diameter, residing within a very narrow gap in the ring. The Keeler gap, its gravity is very weak, but sufficient to stir up nearby dust particles as it passes. This creates these wave or ripple effects in the adjacent rings, sometimes even stripping material directly from the ring, as shown by this small trail. These ripples not only move side to side, but also undulate vertically, as shown by the shadows they cast. One can only imagine sitting on Daphnis, watching the waves follow its orbital path, with the magnificent Saturn and its many other moons in the background. What a spectacular sight that would be. Speaking of the rings themselves, Cassini captured some extremely spectacular images. This one shows it to 0.1 full spiral density wave from Janus. Astonishingly, what you see here is the result of the same process that creates spiral galaxies, just one much tighter. What appear to be many separate rings are actually just 2 spiral arms wrapped many times around the planet. So in the image, every other line you see belongs to the same spiral arm. This image is part of the arm ring located at a position within the ring, where the orbital period of the material is half that of the moon Janus's orbital period, thus triggering an orbital resonance. This photo gives an illusion as if the top left of the image is tilting away into the distance. But that's not the case. This illusion is caused by the way the density wave propagates outward from the resonance point. The wavelength decreases with distance from the resonance point, and this is what makes this resonance even more incredible. The moon causing the resonance. Janus swaps orbital positions with its neighboring moon, Epimetheus, every 4 years. Each time this swap occurs, the rings respond, forming a new crest in the wave. NASA states that the distance between any pair of crests corresponds to the distance the wave traveled downstream from the resonance point over 4 years. This means the waves seen here encode the orbital history of Janus and Epimetheus over decades. According to this interpretation, the waves in the far top left part of the image correspond to the positions of Janus and Epimetheus during the Voyager flybys in 1980 and 1981. That was also the event when Janus and Epimetheus were first confirmed to be 2 distinct bodies. This encoding method is somewhat like recording a tree's age through its rings. It's simply amazing, besides some other beautiful and detailed ring images. Another discovery was these small spiral propeller-like structures dotted in multiple locations within the rings. This image shows both sides of a ring section. The top is the sunlit side. The bottom is the unlit side. Scientists did this for comparison and to try to discern details. Although the image scale is about 500 meters per pixel, the small moonlets likely remain unresolved. You might barely see a trace of it in the top image, but what is visible is this small moonlet physically connected to the ring via this band of material. As mentioned before, this isn't the only one trying to create a gap in the rings. Here is another found right next to the ink gap, and here is another, possibly the largest of these 3. The diameters of these moonlets are believed to be no more than 2 kilometers, with a density possibly like that of a snowball. The last interesting thing Cassini could image within the rings were extremely tiny but solid objects forming around the Av ring. These are likely caused by perturbations from some nearby shepherd moons. They appear to be solid as they persist after multiple impacts with the Av ring. Upon impact, they kick up dust and particles. These particles sometimes even follow their orbits, as indicated by the faint haze around them. The objects themselves are actually invisible due to dust obscuring the view. Finally, let's look at the planet itself. As Cassini flew by, it was high summer in Saturn's northern hemisphere. The famous hexagonal storm around its pole was clearly visible. At the center of the hexagon is a permanent polar vortex with a huge hurricane-like eye wall. Interestingly, the polar color seems to change with the seasons. This can be clearly seen compared to 2012, when the pole appeared quite dull. Using other wavelengths of light, other storms can be seen, dotted across the planet's surface, along with banded structures reminiscent of Jupiter's, just less distinct in natural light. Also, because Cassini was so close to the planet, it could observe the planet's horizon very well. On the left side of the image, a thin haze in the stratosphere is visible. This haze gradually disappears towards the right side of the image. When Cassini entered the atmosphere during its final approach, it was thought it might not even survive down to the altitude of this haze layer. However, scientists weren't too worried about this. Scientists were particularly interested in what the atmosphere was composed of. Cassini would dive into the inner atmosphere to find this information, burning up in the process, sending back its final readings. But 1 week before its atmospheric entry, Cassini was still taking images. Some of these final images were spectacular. Please note, however, Cassini could not capture real-time video. The video I am about to show is a time-lapse, created by stitching together numerous individual images, forming a spectacular visual effect, showing the view as if riding along with Cassini on its final journey into Saturn. Not all these images were solely of Saturn itself. The first time-lapse we'll see was taken on September 8, 2017, just 1 week before Cassini's mission end. One of Cassini's primary focuses during its mission was Enceladus. This is one of the prime candidates in the solar system for potentially harboring life in its subsurface ocean. Cassini discovered over 100 water geysers erupting from this ocean through the moon's crust. This water freezes in the space environment, having now formed a beautiful ring around Saturn. This ring is very faint, only visible when backlit by the sun, and is possibly the bluest naturally occurring object in the solar system. Here is an excellent view of Enceladus affecting the densest part of the ring. You can see the geysers disturbing and replenishing the ring. Cassini's final observation of the Enceladus geysers was captured in this remarkable time-lapse, spanning 14 hours of imaging. On September 11th, Cassini approached the apoapsis of its final orbit and captured this beautiful mosaic in natural light. Visible are Saturn's innermost rings, the D ring, C ring, D ring, A ring, and F ring. Saturn's brief shadow falls upon them. It was summer in Saturn's northern hemisphere at this time. meaning Saturn's famous hexagonal storm was clearly visible. You can also barely notice Saturn's subtle banded structure in natural light. However, what's truly interesting about this image is that Saturn's night side is faintly illuminated. This is due to light reflecting off the rings, meaning on the hemisphere facing the Sun, Saturn's night doesn't become completely dark. Beneath the ring's halo, Saturn is pitch black. As Cassini approached Saturn again on September 12th, it captured images of Saturn's atmosphere near the planet's terminator. Incredibly, due to the low solar angle here, huge cloud structures can be seen, casting shadows stretching for kilometers. You might think this is an extreme close-up of Saturn, but actually what we're seeing is a scene spanning about 5,500 kilometers. Saturn's moon Titan could easily fit within this frame. Cassini drew closer and closer to Saturn. On September 13th, it took one last look at Daphnis, the shepherd moon stabilizing the ring. Daphnis's gravity causes ripples in the ring. Sharp-eyed observers will notice ripples both ahead of and behind the moon. This is due to the different orbital speeds of the ring and the moon. The inner ring orbits faster than Daphnis, meaning the ripples overtake the moon, exposing more ring material to the moon's gravity. On the other hand, the outer ring moves slower than Daphnis, meaning the ripples lag behind the moon. By the time ring material reaches Daphnis's sides again, the ripples have smoothed out. On the same day, Cassini took one last look around the Saturnian system. It captured a view of Titan, a moon it had focused on extensively during its mission. An extraordinary world with a thick nitrogen atmosphere. It also glimpsed the irregular F-ring, barely visible at the bottom of the ring system. As Saturn grew larger in the view, it observed Enceladus one last time, after it disappeared beyond Saturn's limb. For about 40 minutes, Cassini's final photo focused on the region it was about to plunge into. It was night there then, so Saturn was illuminated by light reflected from the rings. Taking photos on the final day wasn't a scientific priority. Although the photos were beautiful, they consumed valuable bandwidth. Scientists wanted every bit of data in real time. Before the probe was destroyed, this was a unique opportunity. We had never probed Saturn like this before. When Cassini first made contact with Saturn's thin atmosphere, its speed was 123,000 kilometers per hour. Cassini's thruster residual fuel was used to adjust its attitude, keeping its antenna pointed at Earth. At this point, Cassini was about 900 kilometers above Saturn's cloud tops. 1 minute later, these thrusters were at maximum thrust. To prevent Cassini from tumbling out of control, Cassini was directly sampling Saturn's atmosphere. But this atmosphere was also heating Cassini. Just 10 seconds later, the thrusters were overwhelmed. Cassini began to tumble. Communication with Earth was lost. At this point, Cassini's onboard computer would have tried to determine what was wrong. Gyroscopes and star trackers would tell the computer it was spinning. It likely entered safe mode, allocating power, attempting to correct its attitude. About 1 minute later, the probe would have completely disintegrated, burning up in Saturn's atmosphere. When the data began arriving on Earth an hour and a half later, this final part of the mission was considered a tremendous success. Cassini recorded direct analysis data from Saturn's atmosphere, its ionosphere data on dust particles in the atmosphere, magnetic field measurements, and perhaps even more yet to be uncovered from the data. And this is the magic of the Cassini mission. It continues to bring surprises as the data it collected is continuously analyzed and re-examined. Scientific papers and new discoveries continue to emerge in the years since the conclusion of this groundbreaking Cassini mission. What have we discovered from its data? Some things Cassini learned about Saturn only made the planet more peculiar. You might think you know Saturn. Its iconic rings are the largest in the solar system. Its hazy yellow surface is both mysterious and easily recognizable. It's the second largest planet, with the lowest density, the sixth from the Sun. Yet Saturn remains an enigma. Beneath its veiled atmosphere lurks a great mystery, revealed by the Cassini probe, a mystery the scientific community still hasn't reached consensus on. Saturn behaves in ways, from its temperature, magnetosphere, even the length of its day, that contradict our existing models of what's possible. What's going on with Saturn, and what are our best attempts to explain these perplexing phenomena? The Cassini probe arrived at this gas giant on July 1st, 2004. It wasn't the first probe to reach Saturn. 3 previous probes had conducted flybys. However, it was the most thorough one, as we've mentioned. It orbited the planet for 13 years, using its various spectrometers, magnetometers, and other instruments to collect vast amounts of data. The knowledge it brought us is a great treasure, but sometimes only deepen Saturn's mysteries. Take the hexagonal storm at Saturn's North Pole, for example. Each side of this 29 0-kilometer-wide storm is large enough to easily accommodate the entire Earth, and as far as we can tell, its longitudinal position remains fixed, moving with the planet's rotation. This is unlike Saturn's other rotating clouds, which are driven by winds up to 1,800 kilometers per hour. This storm is undoubtedly peculiar, and scientists still don't have a complete explanation for it, although some lab experiments have created near hexagonal shapes on a smaller scale. But it's not alone, as the massive amount of data collected over the Cassini mission years was analyzed. More mysteries began to surface. It started with a rather simple question: how long is a day on Saturn? Despite observing Saturn for millennia, scientists still had no definitive answer. After all, it's not as simple as looking up at the planet and measuring how long it takes for a rocky core to rotate. Saturn's thick cloud layers obscure any potential landmarks on a solid surface below, and due to strong winds, these cloud layers move at different speeds than the core. The rings themselves orbit Saturn at different speeds, so they couldn't solve the problem either. You can't infer the planet's rotation speed by observing their orbital speed. After all, most moons don't do that, and the rings are no exception. However, scientists have techniques to determine the rotation period of gas giants by observing their magnetic fields. They had hoped this method would work for Saturn. Planets with magnetic fields generate them via the dynamo effect as the planet rotates. Liquid metals in the core spin and move. This fast molecular motion generates huge electrical currents, which in turn produce the magnetic field. One characteristic is that, due to this rotation, the magnetic poles are always offset from the planet's actual rotation axis. If the two coincided, the magnetic field couldn't persist for long, so you just need to detect the magnetic field around the planet. Cassini could do that and observe the magnetic poles moving in a circle around the planet's true rotation axis. Once the magnetic pole completes one rotation, you have the length of a day. However, Saturn clearly doesn't play by the rules. Its magnetic poles are almost perfectly aligned with its rotation axis by less than 0.1 degrees. Even though dynamo theory claims this should be impossible, Saturn's magnetic field is very much alive. Its magnetic moment is 580 times stronger than Earth's and holds significant influence over the entire Saturnian system. Scientists don't know how this magnetic field is generated because it's impossible under dynamo theory, and there's no other proven method to generate such a strong field. Either the planetary dynamo effect is indeed at work in Saturn's core, but some other effect in the atmosphere is distorting the magnetic field lines, aligning them perfectly with the rotation axis, or we are observing a completely new method of magnetic field generation on Saturn. Thus, solving the length of Saturn's day was back to square one. Fortunately, radiation proved more helpful. Saturn is an electrically active system. Charged ions move between various layers within its atmosphere, and even between its rings and ionosphere. Scientists noticed that, due to all this magnetic activity, Saturn emits radio waves, and the intensity of these radio waves fluctuates periodically. In fact, this seemed to reflect what might be produced by the planet's rotation. Approximately every 11 hours or so, a peak in radiation levels would occur. Therefore, scientists concluded with reasonable certainty that this was the length of a Saturnian day. Their initial estimate, based on Voyager data, was 10 hours, 39 minutes, 23 seconds. It was hoped that Cassini would refine this number's precision. Initially, Cassini did, but then things got very strange. Because over the 13 years Cassini studied Saturn, this number began to change. It drifted by about 1% over a year, sometimes increasing, sometimes decreasing. This almost implied that the planet's rotation speed itself was changing, sometimes speeding up, sometimes slowing down. To be clear, a planet as massive as Saturn should not do this. Therefore, scientists concluded this wasn't happening. Some effect must be confusing Saturn's data again. Some aspect of the atmosphere was causing the magnetic field to vary, making the radiation fluctuate over time, hiding the planet's true rotation beneath a layer of shimmering camouflage. Another key consequence of the planetary magnetic field is the auroras shining at Saturn's poles. But on Earth, our auroras are the result of the solar wind interacting with our atmosphere. It's thought this doesn't fully explain the auroras on Saturn. Cassini detected that at least some auroral occurrences were unrelated to solar wind activity at the time. This means Saturn's auroras aren't solely sun-driven. Something strange must be happening inside Saturn It's also hotter than it should be. It radiates about twice as much energy into space as it receives from the sun. While some of this might be due to gravitational compression, the rest requires another explanation. Ultimately, all of this needs a unified explanation. Thanks to Cassini's data, we found the key to all this might lie within Saturn's gaseous atmosphere. Saturn is a gas giant. It's almost entirely composed of hydrogen and helium, about 75% of the former and 25% of the latter, mixed with some other trace elements. Not all of this is in gaseous form, because Saturn's enormous. Mass means the deeper into its atmosphere you go, the greater the heat and pressure it's thought. This pressure forces gaseous hydrogen into liquid metallic hydrogen. Some scientists speculate that this liquid hydrogen might even be so compressed that hydrogen turns into diamond, raining down into Saturn's depths. The resulting friction explains some of Saturn's anomalous heat, but the rest of the heat comes from the auroras. While the understanding of auroras is incomplete, it's thought they are the product of charged particles entering Saturn from its rings and moons. Whatever the source, these auroras likely generate enough heat to warm Saturn's upper atmosphere. Such high temperatures produce other effects. Where warm and cold wines meet, strong wines form. It's hypothesized these wines carry charged ions high into Saturn's atmosphere, and it's these charged wines that distort the data from Saturn's radiation, causing it to vary. Perhaps this movement of electrical current could also explain why Saturn's magnetic field isn't where it should be. This might be caused by a conductive layer in Saturn's clouds moving at a different speed than other layers, thus generating its own magnetic field. At least that's what one explanation suggests. Bringing all this together, it should be clear that most of these explanations lack definitive proof. Scientists are sifting through the data provided by Cassini, hoping to gain further insights. If these insights don't emerge, then eventually another mission to Saturn will be needed to find the answers to these puzzling questions. But what about the length of Saturn's day? Thankfully, this mystery does have an answer, and it turns out the clues were in the rings after all. Scientists realized Saturn doesn't just influence its rings through electromagnetic effects, but also through gravitational pull. That's fairly obvious, but more insightful was that Saturn doesn't pull on them evenly. Saturn isn't a perfect sphere. Any variations in its shape cause variations in its gravitational field. Saturn's rings are the perfect canvas for detecting these variations. As Saturn pulls on its rings with varying strength at certain positions within the rings, we should be able to detect ripples. Scientists began searching for these ripples and successfully located them by measuring the distance between them. They were finally able to calculate the length of a Saturnian day. The result wasn't far from previous estimates: 10 hours, 33 minutes, 38 seconds. And this time, scientists are quite confident they got the right answer, so at least that mystery is solved. However, Saturn's other mysteries remain. The next mission to Saturn will be launched by NASA's Dragonfly in 2027, although this mission will focus more on exploring Saturn's largest moon, Titan. Titan is the most Earth-like body in the solar system. as it's the only one thought to have a substantial nitrogen-rich atmosphere, similar to ours though without oxygen, and has a rainfall cycle and liquid lakes on its surface, though of methane, not water. Therefore, it's understandable scientists want to explore it. However, this means it might be quite some time before Saturn's deepest mysteries are unraveled. Saturn breathes winds that may prove to be the lifeline of this system, howl and flow high in its atmosphere, its subtly balanced magnetic and gravitational fields gently act upon its rings, keeping them perfectly arranged. Saturn's rings are thought to be surprisingly young. Saturn itself may be over 1 billion years old, but evidence suggests the rings might have formed only in the last 100 million years, and they are slowly draining back into Saturn's atmosphere. So in another 100 billion years, they might be gone. If humanity hadn't appeared in our era, we might have missed this magnificent cosmic spectacle. And to see those mysteries and wonders, all the beauty, all the scientific data, none of it would have been possible without the incredible Cassini-Huygens mission. It truly is one of the greatest space missions of our time. All right, my friend, let's conclude our conversation here for tonight. Now, allow me to press pause for you, set aside all thoughts and inquiries, and simply be present in this moment. From here, my words will fade away, leaving only the silent tapestry of the cosmos and a carefully curated piece of pure music tuned to 430 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into a state of deep relaxation. Now, find your most comfortable position. Gently close your eyes, or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night and sweet dreams until we meet again among the stars. Thank you.
you.